Hello, everybody. What we're going to be working on today is a review of the Algebra 1 standards on statistics. This is all stuff that, according to the state, you were supposed to be taught, but wasn't tested 2 years ago. And in the rush at the end, a lot of people didn't get this material. And so I just want to do a quick overview of it. We don't have to know how to do all this stuff for Algebra 2, but we need to be aware of it, or else what we're going to do next does not make sense. All right, first of all, most of you are familiar with this, but we're going to see some symbols that you may not have seen before. And those are all going to be part of the Greek alphabet. If you go to college and you pledge fraternity or sorority, these will become very important. But the big ones we're going to be working with today is this one, which is mu, and this one here, which is sigma. And so we call this mu, and we call this sigma. Some other ones you may recognize are delta, pi, lambda. Capital sigma is one that we'll get to a lot. We'll see today as well, and in a few units coming up. All right, one of the central things, if you do take a statistics class, is that there's a big difference between the census of a population, where you count or measure everybody there, and the sample of a population, where you're just taking a small group. Ideally, everything would be a census, but that's not always possible. Let's say we wanted to know the average size of a fish in Lake Michigan. Well, it'd be impossible for us to take a census. We'd have to drain the lake, collect every single fish, and measure it. So that's not really going to work. And so in statistics, there's a big difference between a census and a sample. We're not going to get into that a lot in Algebra 2, but it's important to be aware of the difference as we move forward in other math classes. So the first thing we're going to talk about is how we quantify a large set of data. How do we look at it? And that's really what stats is. It's taking a whole lot of information and trying to make it simple so that we can understand what's going on. The first thing you're supposed to have been taught in Algebra 1, and you probably learned this in elementary school several times over, was how to find the mean, which is most of you will just know as the average. All right? Now, we are primarily going to use mu here, because we're always going to refer to our population mean. We're going to take an entire population, add them all up, and then divide by the number of people there. In statistics, if you use a sample, we use this symbol instead, and you say that as X bar. But don't worry, we're going to stick primarily with mu here. Now, this is just a fancy symbol for what you already know how to do. How do you find average? You take all the individual items and you add them up. And that's what this symbol here means. This is the capital letter sigma, just means to add everything up. So you would add up all the values, and then you would divide them by n, where n is the number of things in the population. And while this formula is kind of scary, we all know how to do this. All right, so we have the foot length in centimeters of 7 14-year-olds in a class in the United Kingdom. Someone sat down, and there's a class with only 7 kids in it, and they measured the length of their foot in centimeters. They had them stand on the ruler, and they looked. So how do we find the mean? Well, we're going to go 25 plus 22 plus 20 plus 25, plus 24, plus 24, plus 28, and then we're going to divide that whole big number by 7. And I'd like you to try and do this in your calculators along with me. And you'll get 168 over 7, which if you put in your calculator comes out to be exactly 24. Now it's very important that we consider units here. So we would say, since these are the foot lengths, we would say mu equals 24 centimeters. The average of the population is 24 centimeters. Units are going to be important in some of the stuff. Answers don't have meaning in word problems unless we write the units in. Now, one of the cool things about mean is if we look at it, it also works as the balance point. And what we're going to do here is what's known as a dot plot. So I'm going to put a dot over 25 because there was one student who had a foot length of 25. I'm going to put a dot over 22, a dot over 20, another dot over 25, so I put this one on top of the other one, 2 at 24, and then 1 out at 28. Now, as we said before, we said the mu was 24. That was the average. And what would happen is if we were to put this on something, this would balance. Because even though there's only 2 things on this side of the mean, and there's 3 things on this side, these 2 are further away from the mean. And so if we actually set up a ruler and put these out, this would your data set will always balance on the mean. All right, so mean was where the center of the data was. That tells us where the center. But that doesn't tell us enough. We also need to know how spread out the data is. Not just where the center of it is, but how spread out. And so the units we use, or the way we measure that, is using something known as standard deviation. And once again, there's a difference in the symbols we use for a population as opposed to a sample. In a population, we use lowercase sigma. In a sample, we use what's known as S sub x. The good news is in Algebra 2, all we'll be using is the sigma for our standard deviations. So what do we mean when we talk about deviations? Well, a deviation is how far something is away from the mean. So this is our data set from before, and we said mu was 24. So the first point down here has a deviation of -4 because it is 4 away from the mean. The data point of 22 has a deviation of -2. At 24, all the deviations are 0. So we have 2 that deviate 0 from the mean. Here we have 25, so we have 2 different data points that are one greater than the mean. And over here at 28, we have a data point that is 4 away from the mean. So what happens if we add up all our deviations? Well, what is -4 plus -2 plus 0 plus 0 plus 1 plus 1 plus 4? Well, if we add all those up, we'll get 0. And a funny thing happens. No matter what our data set is, the sum of the deviations is always 0. And that goes back to what we said before, that the average is always the balance point. That's always going to be the center. And in order to balance something, for everything you have on the left of the mean, you're going to have something equally far away on the right. And it's like the teeter-totter, right? If you had one big kid on one side, you had to have 2 small kids on the other side so that it would balance. And we're going to see the same thing here. So the only way that this is going to make any sense is if we figure out some way to turn all the deviations to positive values and then add them up and average them, because that would tell us how spread out the data is. So the question becomes, how do we turn the deviations positive? And we've learned two different functions in this class that will take a negative number and always turn it into a positive number. And the first one is absolute value. And if you took Algebra 1 right now, they would teach you something called mean absolute deviation as a stepping stone to understand what standard deviation is. There is another function, though, that we learned, and that is if you square something, the answer always comes out positive. And so that's what we're going to use, and this is what the statisticians who developed all the math behind statistics use, was that they squared the deviations. And they created a formula for something called the variance. And the variance of the population is how variable the data is. And this formula up here looks awful, but it's really not that bad. This right here were those numbers we wrote on the board before, the -4, the -2, the 0, the 1, and the 4. That's how far away things are from the mean. And so what this formula is doing is saying square them, then add them up. So let's go back and do that. So we're going to take each one of these and we're going to square it. So I get 16, 4, 0, 1 and 1, and 16. And if I add up all those numbers, I get 38. So this would be 38. And then it's saying, hey, just divide that number by the number of things in the data set. And so in this situation, the variance, which we write as sigma squared because we squared everything here, would be 5.429 approximately. The question then is, what are the units on this measure? Well, it's not centimeters because I squared everything. The units on the variance is centimeters squared. Now that's not really useful because the units we were measuring were centimeters. And statisticians figured out that this wasn't very useful, and so they created one more unit, which is standard deviation. This formula looks bad, but if we go back, it's just the square root of that, of the variance formula. So if we take our variance and we just take the square root of it, that will give us the standard deviation. And I get a standard deviation of 2.33. And here's the good news. The units are centimeters. Now, at this point, I'm guessing half people in class are freaking out because there's no way that they're going to be able to calculate that. And I got good news. In Algebra 2, we're not going to make you calculate this. And if I did, I'd let you use the calculator, which is going to do it for you. So, but I want you to be aware of where these things come from. And then you're going to have to define these things in the worksheet that the sub gave you. So, what does the standard deviation represent? Well, come on. It represents the average distance of any individual observation away from the mean. So average was where the center was. Standard deviation is, on average, how far things are away from the center. If everything's clumped together, their average from the center is going to be very small, and there's going to be a low standard deviation. So if I had a, let's go back to those dot plots. If I had a dot plot that looked like that, right? This is the center. None of the values are going to be very far from the mean. On the other hand, if I have a different dot plot like this, the center is going to be in exactly the same place, but the second one is going to have a much higher standard deviation because the data is spread out, because on average, each one of these data points is further from the center. Now, this is just a quick warning that early on I told you that this is the standard deviation of a sample and this is the standard deviation of a population. And this gets tricky. Don't worry about it. It doesn't play into part in this class. But the standard deviation of a sample has a slightly different formula. You will not know that, but the calculator gives you both when you use the stats package, so you need to know to look for the standard deviation of a population. Now, the good news is you can do all of this on your calculator. We will go to our old friend, the list, and put all of the data points into L1. So you would put the 22, the 20, the 25, the 24, the 28, sorry, you have to put 24 twice, and 28 into L1. Then when you go to calc, and this should remember this from finding our line of regression, our quadratic regressions, all those things, the very first option is one variable stats. And if you choose that, this menu comes up. And it's saying, hey, we'll do the stats on L1, ignore frequency for now, that's not going to be something we use here. And so we would just select calculate. And if you do that, lo and behold, look what we get. The average is 24, and the standard deviation is 2.3299, which is, I said 2.33. I think we're close enough. If you needed to do anything else, like say a box and whisker plot or something else, you will notice that it will also give you the minimum, the first quartile, the median, the third quartile, and the max. And that's if you arrow down. But for now, I just need you to be able to put things in the calculator and find them like that. And you will be asked to do that on the worksheet. So, reviewing, put them all into L1, and then just do calculate one var stats. And you will get the average and the standard deviation. Now, as a word of warning, is you will notice that it doesn't use the symbol mu here. It uses X bar. And remember, that's okay because the two formulas are the same. It does, however, give us both S sub x and sigma because they're different, and this is the one that you're going to want to use in this class. If you were to take another stats class, you would have to look at the situation to see which one you are going to use. So, next up what we're going to talk about is a funny little anecdote. If you ever go to Boston, one of the premier universities for science and math in the United States is MIT, the Massachusetts Institute of Technology. And it's located in Cambridge, Massachusetts, across a bridge from Boston. The body of water here is the Charles River. And if you go into Boston, you have to walk across this big, long bridge across what's known as the Charles River Basin. And there was Boston in winter is not the most pleasant place. It is cold and it is windy, especially if you're going across this bridge, across the basin where it's wide open. Excuse the interruption for a second.
Mr. Chris, please call the main office. Mr. Chris, please call the main office.
So the story was there was a gentleman who was at MIT, who was the head of his fraternity, walking across this bridge in April in 1959. And it was cold. And the wind was howling. And so he had his head down. And the bridge is quite long. The bridge is, I can't remember exactly, I think like a half mile long or maybe a quarter mile. It's a long time to be walking out with the wind blowing on you. And he had his head down, and he was like, oh my gosh, how much further do I have to go across the bridge? I don't even want to look up because it's so cold. And he decided that what he really wanted to know is he wanted something to mark out how far across the bridge is. So when he got back to his fraternity, he got all his fraternity freshmen together, and he said, all right, guys, I want you to go paint on the bridge how far across it is. And they asked, okay, them being some of the biggest nerds in the country, asked, okay, what do you want the units to be? Meters, feet, whatever. And the fraternity president got a little smile on his face, and he looked at them all, and he looked at the shortest guy. And the shortest guy was Oliver Smoot. And he said, I want you to measure the bridge length in smoots. And I looked at him and said, what? He's like, I want you to have Smoot lay down at one end of the bridge, and I want you to make a mark at his head, and then I want you to have him go up, and I want you to just mark how many smoots it is across the bridge. And so they went out, and they had him actually lie down, and they'd make a mark at his feet, and they'd mark a mark at his head, and then he'd lay down again, and every 10 smoots, they'd say 10 smoots, and every so forth and so on, until you got to something that looked like this. And this is, at this point on the bridge, he had laid down 100 times. As it turns out, Oliver Smoot was 5 feet 7 inches, and so every 5 feet 7 inches is a little mark on the bridge going across. Now, in and of itself, a smoot is meaningless. No one is ever going to use this unit of measure anywhere else in the world. But on the bridge, it meant something, because you knew, all of a sudden everybody knew as they were looking down how far left on the bridge. They knew the bridge was a certain number of smoots long, and so they knew when they got to 100 smoots, they were a third of the way across. And a funny thing started to happen. When there was an accident on the bridge, they'd call the tow truck and say, hey, I'm at the 75 smoot mark. The cops would call and say, hey, there was an accident, and in their official documentations for the accident, they would say what smoot mark they were at. And so while it wasn't useful anywhere else, it was very useful on this long bridge in the basin. As long as you were comparing smoots to other smoots, it worked great. To the point that when they redecked the bridge around 40 years later, they actually made this concrete joints, instead of being 6 feet, 5 feet 7 inches, and so the concrete joints are exactly 1 smoot long on the Harvard Bridge. Even though the Harvard Bridge does not actually go to Harvard, it goes to MIT. Now, why am I telling you this story? Well, because we use feet to measure length. And that eventually came because it was kind of the average foot length for a person. If you put your feet across, one in front of the other, you could get approximate distances. And that wasn't real exact, but that's the basis for the English standard of measure. But what would happen, say, if we were all living Avatar, and we were, one of the blue skin guys, Na'vi, I believe? Well, they all have giant feet, so would their feet be the same as our feet? No. But approximately would they be the same number of feet tall? Maybe, because they had bigger feet. And so this is all lead up to something called a z-score. And the z-score is how do you compare apples and oranges? And you've always heard that. You can't compare apples and oranges. Well, actually, you can. We can't compare an apple to an orange, but we can compare apples to other apples and say this is a good apple. And we can compare oranges to other oranges and say this is an okay apple, and therefore this is a better apple than an okay orange. Let me explain that differently. You all have teachers that are easy, and you all have teachers that are hard. And we all know there's classes where you could basically die during class and probably still get an A. And we know there's another class that no matter how hard you work, no matter how hard you try, you're probably never going to do better than a B. Don't say names. I don't want to know. So here is a scenario. You take 2 classes. You have Mr. Easy Grade for history. And you take a test in his class. And on the same day, you take a test in Miss Hard-Nose's English class. And you get back your results. So in Mr. Easy Grade's class, he actually posts the results and he says, hey, the average score was an 87. So Sorry for the interruption.
Mr. Pitts, please call the main office. Mr. Pitts.
So the average grade in Mr. Easy Grade's class was an 87. And the standard deviation in Mr. Easy Grade's class was a 6.85. The average grade in Miss Hardnose's class was a 71, and the standard deviation in Miss Hardnose's class was an 8.5. You get an 94 on the history test and an 85 on the English test. These are actually your grades. And so the question then becomes, whose class did you actually do better in? Well, as it turns out, we have a way of measuring this. Because what we can do is, a standard deviation is how far on average things are away from the center. So we have a unit, what's known as, and this is just a summary of what I just wrote down, of something called a z-score. And a z-score is taking your score, subtracting the average, and dividing by the standard deviations. And that sounds crazy, but let's try it. So, your z-score for Class A is going to be 94 minus 87 divided by 6.85. And if you do that in your calculator, you get a z-score of 1.022. On the other hand, the z-score for, and this was Mr. Easy Grade, and this is Mrs. Hardnose. And in Mrs. Hardnose class, your score is 85 minus 71 divided by 8.5. And your z-score is a 1.647. Now, what do those numbers represent? Well, your standard deviation is, your z-score, your z-score is how many standard deviations an individual thing was above the mean. So, in Mr. Easy Grade's class, you did better than the rest of the class, but you did one standard deviation better than the class. In Miss Hardnose's class, you did 1.647 standard deviations better than the class. So you were better, and better compared to the rest of your peers. So you did better than the class in Miss Hardnose's class than you did in Mr. Easy Grade's class, even though your grade was higher in Mr. Easy Grade's. And so that's an example of how we use z-score to compare things that are not alike. Right? So now we've gotten our basic gist of what you were supposed to have learned in Algebra 2 and Stats. And once again, it's not critical. I would like a little bit of experience with this, but mainly we need to understand what a mean is, what a standard deviation is, and what a z-score is, so we can start talking about the stats unit next class. Everybody enjoy your Monday, finish your worksheet, and don't give the substitute any trouble.